In this video we're going to derive the divergence in cylindrical coordinates. Now you'll see that I've drawn a little section of a cylinder here, so we've got our x, our y and our z axes. Now in cylindrical coordinates there's only going to be replaced with z's, which remains the same, and a distance r and an angle of theta. So you can see then that this little volume element here we have of the cylinder is going to be given by our distance delta r times the height here, delta z, times the distance round in this arc. Well, the distance of the arc is going to be given by r delta theta. So it means that the volume element here is going to be given by delta r, delta z, r delta theta. Now what we're interested in is the flux through all the 6 surfaces of this little section of a cylinder. Now the flux is going to be given by the surface integral of the normal component of a field. So let's rewrite this out again. So I've drawn it out again. What we're interested in is the front surface here, surface 1, and the back surface here, surface 2. Okay, so that's the front surface, the curved surface at the front here of this, and the curved surface at the back side of it. So you've noticed that the normal components are facing in the opposite directions. So whenever we take the vector function and we form the dot product with that vector function with the normal component, then the other 2 components, there's only one component left at the end, so they're only being left with our component of our function in the r direction, because the dot products with the components in the z direction and in the theta direction are going to disappear. Okay, so because you'll just have, for example, I dot I, which will remain, which would be a f of r, and the I dot j would give us a 0, and an I dot k would give us 0. Okay, so only one component left. So write that component out then as the surface integral of the fr component of a function by ds for area element 1. Now, in order to work out this surface integral, we can approximate it by looking at the value of the function on this front surface in the n direction and multiply it by the area of the surface. Excuse me. So what we'll have then is the point at the front here. Well, the point at the front is given by our function f of r at the front surface. Now the front surface is going to be given by r plus delta r upon 2, and you can see that up here because our r actually comes to the centre of this little section here, and then we're adding on a delta r upon 2 in order to get to the front face, and the theta and z will remain the same. So that's just telling us the position of the value of the function f of r. Okay, so that gives us the value of the function at that point there. Now we're going to multiply that by the area of the face. So the area of the face, well, it's just going to be the height delta z times the distance round in the arc. Now that distance round an arc is going to be r delta theta, but remember that r we're looking at is the r for the front face. So the r for the front face is going to be r plus the value of delta r upon 2. So we're going to have r plus delta r upon 2, delta theta, delta z. So that just gives us the area component and the value of the function f of r. Now we do the same for the back face. The only difference in the back face is the normal component points in the opposite direction. So the normal component is going to give us a value of minus fr, and also the back face is going to be given by our distance r minus the delta r upon 2 to get to this point here. And the theta and the z remain the same, and of course the area is going to be the same again. It's going to be our delta theta, delta z, but this time it's going to be the r distance is going to be r minus delta r upon 2, which will take us to this little point here. So now what we can do is we can add both of these together in order to get the flux through surface 1 and 2. So when we add these two together, we take out the common factor of delta theta, delta z, we get this little equation here. Now what we can also do is we can multiply this top line of this thing here by r delta r and the bottom line by r delta r. So in doing so, we haven't changed the equation, in any way, but you'll notice now that the top line here, r, delta theta, delta z, is actually the volume element here, delta V. So what we can do then is we can form our flux at a single point by taking the limit as delta V tends to 0 of 1 upon V of the surface integral of 1 surface 1 plus 2 of the normal component of the function. And you'll notice then this delta V here, well, that delta V is going to be the top line here. Okay, so it means that whenever we take this limit here, this top line here disappears and we're just going to be left with our 1 upon r delta r. Now when we take this limit here, the delta r, you'll notice, is in the bottom line here with the delta r here and the delta r. So when we take that limit there, we're simply left with the value of our 1 upon r, and it's going to be the partial by partial r of, well, what's left here is the delta r tends to 0, so we're going to have our value of r here. So it's going to be r times the value of function f of r. Okay, so that means this is the first part of our derivation of the divergence in cylindrical coordinates. Now we're interested also in faces 3 and 4, and we'll go through a similar process with faces 3 and 4. We'll notice that now we're interested in not the variation with respect to r, we're interested in the variation with respect to our angle theta. So if we come back up here, you'll see we're interested in this face here and the other face at the other end here. So what's going to be varying here is our angle theta. So when we rewrite this here, we can see that the only component of the vector function in this direction is the component f of theta. So we're going to have our vector function f of theta, and it's going to be approximately equal to, well, again, we're going to work with the centre of this face times the area of the face. So it's the value of the function at the centre of this face in that direction theta times the area of the face. Now the position is going to be r, but the new position is going to be theta plus delta theta upon 2. Okay, so the theta plus, that's the angle theta, plus the delta theta upon 2 will take us to this point over here. Okay, so it's the far end of this face. So we have to then we'll take out the common factor again of in this case the common factor for the area. Well, the area is going to be delta r times just our delta z. Okay, so that's just this area here, so it's that height times that distance there. Again, you can see that up here. It's just this small area here, which is delta r times the delta z. But we can do the same trick as we did in the previous section here. We can multiply this time by r delta theta upon r delta theta, and it doesn't change this equation at all. And we'll notice now that the top line here is going to be our r delta theta delta z, which again is the volume element. And if we were to take the flux at a point, we're looking at the limit as delta v tends to 0 of the surface integral of the normal component of the field over faces 3 and 4. So this factor here, well, that's just the partial derivative of f of theta. So we're going to have partial f of theta by partial theta, and we're going to be multiplying by, well, the value of r. Of course, the delta theta here just gets subsumed within this partial derivative. So that's going to give us our second component of the cylindrical coordinates. And finally, the third component, we're interested in the value of the normal components in face 5 and face 6. So that's looking at, and back up here, that's looking at the top face here and the bottom face here. So what we're interested in then is the only part of the component of the vector field that's in this direction is the z component. So we're interested in looking at the point in the centre of the face and the value of the function at that point times the area of the face. So we're interested in r, theta and z plus delta z upon 2 minus the same point in the other side of the face, which is going to be minus f of z, r theta z, minus delta z upon 2. Okay, so that's just giving you the value of the function at points 5 and 0.6 above here. And we're going to multiply it by the area. Well, the area is just going to be the r delta theta delta r, and you can see that there. So there is going to be our r delta, it's going to be this distance here times this distance. Now that distance there is going to be delta r, and we're going to have our r delta theta is going to be this little distance in here. Okay, so that's going to give us this area. So what we can do then is we can take this area r delta theta delta r, and we can multiply it by, this time now, is delta z upon delta z. Doesn't change the value of the function, but we'll notice the top line now is given as a volume of the small element. So we can go and we can look at the divergence at a point by taking the limit as the volume tends to 0, 1 upon the delta v. So the delta v here is what's going to be the top line of this function here. So we're just going to be left with delta z at the bottom. The delta z is going to be coming in here and get subsumed within the partial derivative. So when we take the surface integral of areas 5 and 6 of the vector function and normal component, which is the flux, we're just going to get the partial integral of fz by delta z. So that's the final part of it here. So finally, when we take all of those three and we'll add them together, we get the divergence in cylindrical coordinates. So the divergence of a vector field f, a vector function f, is going to equal 1 upon r partial by partial r of r times f of r plus 1 upon r partial f of theta upon partial theta plus partial f of z upon partial z. So I hope you enjoyed this video. I hope it was of use. In the next video we'll go on and we'll do the same thing, only in cylindrical and the spherical coordinates, and it's very similar type of derivation. So thank you for listening and goodbye.